So this is a half a millimeter, a quarter of a millimeter for scale. For those who aren't familiar with metric, a quarter of a millimeter is about 1/100th of an inch. And the largest size you see in this image, these go from about 125 microns to 250 microns. The largest ones you see here are about 1/100th of an inch. You can see they're nice and shiny, and these are what are made by impacts. Okay, now this is an illustration of a possible Cretaceous-Tertiary boundary impact. It's a 10-kilometer asteroid hitting just off the Yucatan Peninsula. This thing's 10 kilometers long, but it's coming in at 20 kilometers per second. So it's going to penetrate into the Earth's crust, basically in less than a second. This is a very energetic event. It's going to dig a crater that's probably at least 100 times the volume of this asteroid. The Yucatan crater is 180 kilometers in diameter, about 200 kilometers in diameter, 20 times the size of this asteroid. There's going to be a shock wave that's going to blow. As the front is hitting, the back doesn't even know. There's going to be a shock wave that blows through this thing, disrupt it, put it under very high pressure, very high temperatures. It will blow off a little bit of the backside. The backside may not even get melted or anything, but most of it's going to be very severely disrupted. And I'm going to try and show you a few slides at this point, what happens basically during an impact. Now, this is an illustration from a magazine that was published several years ago. It was artist's concept of a huge asteroid impact. It's got the scale kind of right, maybe a bit too big if you think of this as Long Island or maybe Baja, California or something. It's a couple hundred kilometers across. But what the illustrator got wrong here is not like a nuclear explosion that just rises to the top of the troposphere and forms a mushroom cloud. The asteroid impact is so energetic, it's going to blow things up out above the atmosphere. This illustration gets it a little bit closer, although it still misses what's going on in the middle. Around the edges, there's going to be this huge volume of material that's going to be ejected out to the sides. It's going to form a thing called an ejective blanket. Most of the mass ejected that's excavated from the crater will be ejected and deposited within a few diameters of the crater. So for a 200-kilometer diameter crater, most of it's going to be within 600, 700, up to 1,000 kilometers or so. There's still a lot, probably up to a couple thousand kilometers. But some of the stuff's going to blow out through the middle, up above the atmosphere, and get transported around the planet and form what we call the distal impact ejecta deposit. And that's the part that I'm really interested in. And that's where all the spherules are. This is an illustration, just to kind of give you an idea here, of a computer model that Betty Pirazzo did several years ago. She tried to simulate on a computer the impact of a 10-kilometer diameter asteroid into the Yucatan Peninsula, where there's a thin layer of water, a few kilometers of sediments, and then very hard rock granite underneath it. She modeled this as being dunite, which is basically an olivine asteroid. And you can see it's orange, and it'll look that way in the simulation. The orange will be asteroid. The lighter colors will be layers of sediment, and the darker stuff will be the granite. And this is actually a very oversimplified model. It's coming in at a 90-degree angle. It's a two-dimensional model. It's not even three-dimensional, but that's about what our computers could handle. And this is what it looks like in the first half a minute. These various images show after 2 seconds, after 5 seconds, after 15 seconds, and then after 30 seconds, what's going on in this impact according to this simulation. You can see that after 2 seconds, the asteroid's already penetrated into the crust and well into the granite. Typical impact, the asteroid will penetrate to a stagnation depth of about 20 kilometers. That's about how deep it will get. And then it will begin rebounding back, but the crater will continue to form out to a distance of this, in this case, in the 30 seconds all the way across. So it's gonna be a couple hundred kilometers across. So this isn't even showing you the full development of the crater. Now you see there's two halves to this image. One has got all these arrows in it, and the other half doesn't have arrows, so it has these lines. These are contours. These are density contours. There's much less amount of material here. So this is lower density. As you go toward the edge, there's higher and higher density. And you can see here, this is getting really dense. This is this thick ejective blanket coming out and going out to the sides here. Most of the lighter colored stuff, this is coming from sediments, and this orange stuff is coming from the asteroid. And you're getting a lot of asteroidal material, a mix of asteroidal and sediments really going pretty much straight up. And that's a lot of what's going to be getting distributed globally. These arrows here are velocity vectors. On each image, shows the size of these. Each one is 5 kilometers per second. And you can see some of these, these are longer than 5 kilometers per second, especially early on. Some of these are getting up to 7, 8 kilometers per second in this model. Undoubtedly, there's some that'll be faster than that. 8 kilometers is elliptical to get a rocket into low Earth orbit. So this is definitely enough velocity to get it well above the atmosphere and probably into an elliptical orbit that's going to come back and hit the Earth somewhere. Yeah, so that's the important thing. We've got much lower density going pretty much directly straight up, and that's where most of the asteroid material and a lot of the sediment material is going to go. And this is the stuff that's going to get distributed around the planet.
A question?
Sure.
In the illustration, is the asteroid coming in from the left side? Is that what we see?
No, it's vertical. It's just coming straight down.
It's vertical?
Yes.
So is there a difference between the two sides?
No.
Just not showing the representation of velocities on the right?
It's just one is representation of velocity here and density here.
Okay.
That's the only difference between them. It's 1,000 times easier to simulate a vertical impact than one coming in from an angle. It just takes the amount of computer power needed to do that wasn't available at the time she did this model. This one was done as a 3-dimensional model by Galen Gisler back about 15 years ago. We did this with a supercomputer down at Los Alamos. And this illustrates, the previous one showed you density, composition, and velocity. This one shows temperatures. And this shows this plume. Here's a 10-kilometer scale marker here. This is 10 seconds after the impact on his illustration. And he's getting temperatures in the range of 10 to 20,000 degrees Kelvin. And once you're getting up to 20,000 degrees Kelvin, it's basically the same as centigrade or Celsius. That's just a rounding error, the difference between them. We're really talking about 20,000 degrees for the temperature of what's coming out of this plume. And so this is what is eventually going to happen to this asteroid when it hits. And now I want to show you some actual examples of the ejecta we get from this. We'll start with the Cretaceous Tertiary, or they call it the Cretaceous Paleogene boundary, but I'm old-fashioned. I like calling it Cretaceous Tertiary, so excuse me if I slip up, even though the Tertiary doesn't really exist anymore in the mind of stratigraphers. This is a lot of localities that have been found for the Cretaceous Tertiary boundary. There's more, not a lot more, in the Indian Ocean that's not on this map. Most of them have been in the Northern Hemisphere. That's where a lot of the research has been done, and it's also closer to the Chicxulub crater. This is where the impact site was here on the Yucatan Peninsula. And I'm going to show you samples from 4 sites. I'll start with the DSDP site 465, which is here. It was on leg 72, but it's site 465. Then I'll go over to southeastern Spain to Agost and show you a boundary layer there. And then Dogie Creek in Wyoming, a non-marine section in the western interior of the United States. That's actually a lot closer to the KT boundary. And then I'll finish up with an illustration of the boundary in the western North Pacific, DSTP site 577. That's got a lot of really nice swirls in it. But this is what, this starting again here, DSTP site 465. This is what the boundary clay looks like, which is a deep sea sediment core recovered at a few kilometers water depth with a coring device. There's a piece that I took out of the core. And you can see this is the boundary clay here. This is only a few millimeters thick. And this is wherever it's well preserved around the world, the best preservation appears to be on the order of about 3 millimeters thick. It's black because it's full of pyrite that has been oxidized. Most sites do have pyrite. The pyrite gets weathered and oxidized though, and it gets this rusty reddish color to it. But this one, because they're mainly under the sea, never really got exposed on land. It's nice and black. You can't really see it here, but there are spherules in here. I've taken small bits of this apart. I find little swirls in it, but they're very highly weathered and they weren't easy to work with. So I haven't really done anything on this one. This is a really nice illustration of the thickness of this boundary clay. This is the southeastern Spain one in Agost. The scale here is a centimeter from here to here. So this thing is a few millimeters thick. It was probably originally a bit thicker than this. It's buried under 10 kilometers sediment and it's been compressed and compacted some. You can't see very well with these kind of circular things here. These are spherules. I'll give you a better look at these in a second here. They're really, because it has been compacted and lithified, turned into a rock, it's a lot harder to see it here. This is basically a hand specimen that's been sawed off flat surface and polished. In most localities, you don't really get a well-preserved layer like this because animals that live in the sediment afterward come in and they burrow through it and they mess it up. They get smeared over long distances. These are actually burrows here. Animals burrowed here. They didn't get the whole thing. They burrowed through it and transported some stuff from up here down to here. But the next picture I'm going to show you is where it's split along the bedding plane, along the bottom of it. We're going to look up at this layer from the bottom. And here's what it looks like. And now you look at it, and you can see all these round things here. The lighter colored ones are easier to see. But these are spherules. There's darker colored ones too. They're not as sharp. It's hard to get spherules out of this particular layer because it's been so well lithified. But this is just to illustrate that this 3 millimeter thick layer is basically made out of spherules. Here's this one from Wyoming. Again, a few millimeters thick. This is non-marine. It was a very gentle environment physically, not very well compacted, but very harsh environment chemically. It was around some coal, which makes it very acidic. The original minerals of these clays are gone. They've been totally replaced by a strontium sulfate called goethite. But you can see this is just very nice, well-distributed spherular layer. And you can see a bit of grading from larger ones here to smaller ones near the top of it. So basically this impact deposit, the Cretaceous Tertiary Boundary, once you get far enough away from the ejective blanket, it's just a layer of spherules. There was certainly some matrix, and that matrix probably was very interesting, but you can't really separate out anymore because it's just so old, it's been altered. We don't really know what the matrix originally was. Oops, I'm going the wrong direction here. Now I'm going to go to the site in the western North Pacific. This is a great place for getting spherules. You get a cubic, there's a deep sea core again. You get a cubic centimeter of this, you can get hundreds of spherules out of it. This is a drawing of the core. The Cretaceous Tertiary Boundary is in here, but this has been messed up by burrowing organisms. See, the Tertiary is kind of dark colored sediment. The Cretaceous is kind of light colored. I kind of blown up part of it here. You can see there's these dark streaks in here, and that's where animals have burrowed and transported some of this down into there. And the light stuff you can see being transported up to here. And it's been pretty thoroughly mixed here. And when you look at so the layer doesn't exist anymore. And many places are like this. And if you look, this is a plot of the microfossil composition here. It starts out 100% Cretaceous. And then as you get through the section here, it gets up to being 100% tertiary microfossils over a range of 10 or 15 centimeters. And you see the Iridium anomaly gets higher and it's extended over 10 plus centimeters. And you even get some Iridium down below the boundary. And that's because the guy who did these analyses, he sampled some of these burrows here that carried some of the sediment down deeper. But this is a great place for, it really has some of the best preserved spherules of anywhere in the world for Cretaceous Tertiary Boundary. I'm going to show you several slides of these. They range in composition and in color. They go from light colored ones to darker colored ones. Most of these I'm going to show you, they're 200 or 300 microns, so about 1/4 of a millimeter or 1/100th of an inch or so in size. And these are the lightest colored ones. I've analyzed bunches of them and measured iridium in them, and it comes out to be about 4 nanograms per gram or 4 parts per billion. In comparison, chondrite, carbonaceous chondrite meteorite, has 450 to 800 nanograms per gram or parts per billion. So this based on the iridium content, might have 1% asteroid in it. So not that much. This stuff is probably made mostly out of sediments, crustal material from the impact site. Here's what one of these looks like when you cut it open. It's made entirely out of clay minerals now. Whatever the original mineral was is gone. But you'll look at this blow up of this here and you see this nice dendritic or fractal-like texture to it. If this was another mineral like a pyroxene, petrologists would tell you, man, this thing crystallized real fast. This is what looks like a quench texture in an igneous or volcanic system. And what we believe these are clay that has replaced the mineral that used to be here, and it's showing evidence of this thing quenching really quickly from a liquid droplet. These are Pyroxene spherules. These also don't have a lot of iridium, maybe 1% asteroid by weight, but they're unique. These are preserved only at this one locality out of all the other in the world where Pyroxene has been preserved. Everywhere else, it certainly was everywhere else, but it hasn't been preserved. It's been altered to clay or something. But we cut these open and we see this white colored stuff. This is Pyroxene. You can see this nice fractal texture to it, the dendritic growth of these things, indicating that these things quenched from a really high temperature. I'm going to kind of go through these quickly now. If you go to darker ones, these are 55%, 55 parts per billion iridium. So, you know, maybe 8 or 10% asteroidal material by weight. And you get more iron-rich ones, and these are maybe 30 to 50% meteoritic material by weight. And again, these are all 200 or 300 microns. The really nice thing about this Site 577, we go down to stuff that's less than 100 microns. So 100 microns is about the width of a human hair. We get to stuff smaller than that. You can still see spherules in there, and a lot of this stuff is spherules, although they are not very well rounded. But there's a lot of little irregular pieces, and we've taken some of these out and analyzed them and found really high iridium content in them, and we've cut them open. And here's just a couple examples. These two actually have more iridium than you find in typical chondrites. This doesn't look at all like a spherule. I think this is like a fragment of the matrix from a carbonaceous chondrite. And so this thing looks like to be like around 70 or 80 microns across. Similar here, I'm not sure what this is, but this has, you know, actually a very high amount of iridium in it. But I think that what we're finding here in the really fine fragments is actually very tiny pieces of the Cretaceous Tertiary asteroid. Now, Natalia mentioned that we found a piece of the asteroid. It was another core not far from here. It was on the same leg, and that piece was like 30 or 40 times as large as these. And it actually had different minerals in it, although they were all altered. Okay, so this is a list of distal impact deposits from a paper recently, 4 or 5 years ago, by Glass and Simonson. And they listed what they considered to be all distal impact deposits ranging in age from the Australasian Microtectites around 0.8 to early Archean stuff at 3.5 billion years ago. Now, I've discussed the Cretaceous Tertiary Boundary in some detail. I'm just going to show you one figure with a map of the Microtectite strewn fields. There's pretty much 3 of them, and they get up to 35 million years old. These are regional, though. None of these are global deposits. The North American Microtectites, 35 million years, is from a crater in Chesapeake Bay that's called the Chesapeake Bay crater. Then I'm going to show you a few slides from Pyroxene spherule deposits. This is also 35 million years and almost the same age as the Chesapeake Bay, but it's from Papagai, which is a much larger crater in northern Siberia. Then I'm going to go way back in time, show you a few. Well, before I do this, I'll go a bit more into the details of the physics of spherules forming. Although it kind of goes over my head, it'll probably go over most of your heads too, so I won't spend too much detail on that. But then I'll go back in time here to the early Proterozoic, to 2.5 billion years ago. There's several spherule beds that Simonson has found, mainly in Western Australia, but a few in South Africa that are the very earliest Proterozoic, right after the Archean, 2.5 billion years old. And then from the Barberton Greenstone Belt in South Africa. and these are 3.2 to almost 3.5 billion years old. And all of these things are made mainly of spherules. This is the Microtectites, the youngest, or the Australasians. There was some sort of an event here around Southeast Asia that created these Microtectites and Tectites. The X's are the Tectites, and the Microtectites are recovered in deep sea cores. There's the Ivory Coast Microtectites from the Basumtwi crater in Western Africa, and the North American Microtectites and Tectites are from the Chesapeake Bay crater here, which is 35 million years old. That's all I'm going to say about them, though. So here's a map, what I'm going to show you. I'll be showing you samples from this late Eocene Pyroxene spheral layer, which has global distribution. I'll show you a map of that in a second. The Kyte boundary sites were from the North Pacific, Wyoming, and Spain, and those are from Chicxulub. The North American Microtectites are from Chesapeake Bay, they're around here. And these late Eocene ones are from Papagai up here. This is 40-kilometer crater, is 100 kilometers, and 2.5 times the size. That's a much, much larger event. And then I'll go show you the Proterozoic ones from Hammersley Basin and the Archean ones from the Barberton Greenstone Belt in South Africa. So these are all the known, well, almost all the known localities for the late Eocene ones. They're mainly equatorial because the equatorial sediments at this age are the ones that have the best microfossils in them, so they're easiest to find the layer. There's also one down here on the Kerguelen Plateau in the southeastern Indian Ocean, and then there's a few on ridges and rises in the South Atlantic. And these are from Papagai, and I'm going to show you a couple of pictures from ODP site 709. This one was great because we got a really big sample of the core. We were able to get a whole heck of a lot of spherules out of it. There's actually 3 types of spherules. There's one they're typical microtectites. They're glassy microtectites. They come as spherules and glass fragments, which are probably broken up pieces of something larger that fragmented when it was traveling through the atmosphere. There's also the Pyroxene spherules, and there's 2 types of these. There's lighter ones, and then there's darker ones. And we've analyzed iridium in bunches of these things, and the Microtectites have the lowest amount of iridium. The light-colored Pyroxene have the next lowest amount, and then the darker-colored ones have the highest amount of iridium. So it looks like these have different proportions of asteroid in them, and they probably also come from different parts of the crust. This was a 100-kilometer impact into Siberia, and there are different rocks in the crust, and these probably, to some degree, reflect different lithologies from the target. And this is just to show you briefly, we've measured the bulk element chemistry of these things. And these are Microtectites, have much lower iron and high aluminum, and the light Pyroxene spherules have higher, I'm trying to see what this is, higher, is that magnesium up there? It's hidden on my screen. And then these are the dark spherules here. They tend to be more calcium and iron. That's calcium up there. Okay. And again, we cut these open. This is a Pyroxene spherule. And again, you see this nice quench texture. These are young enough and in the right sediments sediment environment, they are very well preserved. Some of them are pretty heavily altered, but you get a lot of them like this. They're just full of these Pyroxenes that have this very feathery dendritic texture that shows that they quench. And these often have a little bit of magnetite on the rim, and there's a glass in the matrix here that's still often preserved in these things. So this is just very common for impact deposits. I should mention this late Eocene one, the Kyte boundary was about 3 millimeters, maybe a little bit more thick. This one, it's all, everywhere we found it, it's been burrowed and smeared around. But if you look at how much is in there, the original thickness of this layer when it was deposited was probably on the order of 0.3 of a millimeter, about only 1/10 of the amount of material that's in the Cretaceous Tertiary boundary. Now, just to go a little bit into the physics of how these things form. Oh boy, I'm running a little bit late here. This is a plot from Malash where he did experiments and calculations to try and figure out the equation of state for silicon dioxide, which most of us know is quartz. At room temperature and pressures, Quartz is one of the most common minerals on the surface of the Earth. You raise the temperature and it gets a slightly different crystal form as high quartz. Get it in a hot enough, low pressure environment, you can form cristobalite or tritonite. And if you increase the pressure, it will convert to coesite or stishovite. And you get these by shock also, coesite and stishovite, by shock pressures. Now the pressures on here are gigapascals. I never think in pascals. Probably most of you don't either. But 10 gigapascals is 100,000 atmospheres, or about 100 kilobars for those of you thinking kilobars. So this is very high pressure, 100,000 atmospheres, okay? As you all know, there's three types of matter. This is the solid. There's different crystalline structures. You get it hot enough, it's going to melt and form a liquid. Here we're going to expand it and get it even hotter. Once it melts, it's going to turn into a vapor. So you can get solid, liquid, and gas. Now we've got a log scale, so this kind of stretched out the field for cristobalite and tritonite. But here this is going up to 10 gigapascals, 100,000 atmospheres pressure. And you get up over 3,000 or 4,000 degrees C, it'll turn into a gas. There's also this thing called the critical point. And this is kind of an odd thing for those of you who don't know what it is. At temperatures and pressures above the critical point, it's not even a liquid or a vapor anymore. It's a thing that's called a supercritical liquid that has very odd characteristics, similar to both melts and vapors, and it does other weird things too. On the abstract that got mailed out, you should have had a link to the Wikipedia page on this. You can learn about supercritical fluids if you want, but I wouldn't do a good job of describing it, so I'll leave that to your own study if you want. But let's go on to this next figure here. This expansive, this is that first of these three figures was here. And here's the critical point here. And now we're getting into the range where the impact goes, up to 20,000 degrees, okay, up here. A few hundred gigapascals, which is, this is a few million atmospheres of pressure, okay. We're talking about impact pressures and temperatures up around here. This is an experiment where he shocked a couple plates of silica of quartz together. And what happens is the shock wave goes through it over fractions of a second, just goes up, the shock wave goes through really fast and instantaneously increases the pressure and temperature here. And then it basically vaporizes, it turns the quartz into a supercritical fluid. And that it's up here in the supercritical fluid region, and then it's going to basically expand once the pressure is released, and it's going to follow one of these lines depending on the energy of where it's coming down. And these are called adiabats, and it's some of it'll, depending on how heavily it's shocked, it may come down as a supercritical fluid and then become a vapor. It may come down and become a melt. At some point, it's going to hit this curve, which has vapor and melt on it. And then you'll have melt and vapor together. But the point is, you're going to start with this supercritical fluid. It's come down here, decompress, and at some point you're going to get to a point where there's a mixture of gas and liquid, and it's going to disperse into droplets, and then we're going to work our way down here. Probably in a matter of minutes, it's going to get cool enough, and then it's going to crystallize. It's going to happen really fast, probably in a matter of minutes. And that's where these spherules are coming from. And for different regions in the asteroid, the path it follows may be different, but this is generally what's happening to what's going on in the most shocked part of that asteroid. And we end up with these things. Okay, so now I'm just briefly going to, I see I'm hitting 30 minutes here, so I'm just going to briefly go through the last few slides, show you the Proterozoic and the Archean stuff. This is one of these Proterozoic spheral beds. It's 2.6 billion years old. This is a hand sample that's been sliced and polished, and this is 33 millimeters across, so the larger spherules here are on the order of a millimeter in size. These are larger than the Cretaceous Tertiary Boundary ones. The ones in Australia, most of them are in very shallow water, and it's probably like some sort of tsunami came in and ripped up sediment. You get fragments of sediment that are mixed in with the spherules. So these are all layers of a silt. It was probably sediment farther out on the shelf, and the tsunami came in and ripped it up and deposited it all with these spherules. And here's another one. This is looking down, I believe, on the top of the bed. So this is the bedding plane. and you can see it's just loaded with spherules. And you cut it open. Geologists like to cut these things open and polish them into a microscope slide that's so thin you can transmit light through them. And this is what these things look like. They're just densely packed spheres. They're 2.5 billion years old. None of the original minerals are there anymore, but you can see what look like textures of things that radiated before, and maybe these are rapid crystallization. But these things have iridium in them. Not the Hammersley Basin's one. The iridium isn't particularly high in most of them, but these things are almost certainly from an asteroid impact. And then we get into the Archean. Don Lowe and Gary Byerly spent their career mapping out the parts of the Archean. And in '85, they published a paper where they discovered a spheral bed. They called it S1 because shortly after they found a couple more, S2 and S3, and they found 8 of these now over 25 years or so. And these range in age from 3.2 to almost 3.5 billion years old. The Barberton Greenstone Belt has a sequence of about 8 kilometers of rocks. It's really old stuff. And they found these spheral beds in there. And these are the oldest known evidence of impacts on Earth. And they're probably the evidence of the largest impacts known on Earth. Some of these things are really very thick, very iridium-rich deposits. S3 is the biggest of these. I'll show you a couple slides from that. This is one part of one bed. This bed ranges in thickness typically from 30 to 100 centimeters thick. The spherules are typically more than a millimeter thick. It's a gradation from coarser ones below here to more fine ones at the top. This was probably deposited in a shallow basin, maybe redistributed a bit by light current activity. You don't find anything like this in the Cretaceous-Tertiary boundary. The total amount of iridium in here, the total amount of spherules is hundreds of times more than you find in any Cretaceous-Tertiary boundary, any place on Earth. This is totally unlike anything else. Here's another picture. This is a similar slab that's been cut and polished, and you can just see it's just very densely packed spherules. They've all been totally altered. They were probably altered within the first couple million years after they formed. This was a very hot and volcanic rich environment. But these things are just loaded with iridium. We've also measured other platinum group elements like gold and platinum and osmium and palladium in these things. And we measured chromium isotopes, which prove that these things are definitely extraterrestrial. The iridium signature in here is not coming from the Earth. It is coming from outer space. And there is a heck of a lot of it. And they cut them open, and you see there's spherules. These are also spherules and fragments too here. But what you see here, this is basically all chert or silica, and the brown stuff, this is a clay mineral called cerussite. And so they are totally altered from what they were originally, but they've retained at least the iridium and platinum group elements and the chromium isotopes that were originally deposited. So anyway, I hope I've convinced you that when you have big asteroid impacts, you make these deposits around the planet. And those deposits are, you get iridium in them, but iridium is a few parts per billion. Most of what that thing is made out of is impact spherules. And with that, I guess I'm done. Thank you.
Okay, so let me remove this.
I hope you don't have 50 questions there.
Okay, if someone wants to ask a question, please write on the chat so I will let you speak. So this is to avoid like everybody speaks at the same time. But if you have a question, please write it on the chat or raise your hand. Use the raise hand feature, and I will, or I guess you can unmute yourself if there's no crowd.
Well, I don't know how to raise my hand, but can I ask the question?
Yes.
I'm wondering about how the ages of the spherules are inferred. Is there any direct measurement of their age, or is it inferred from the bedding that they're playing and the age of the bedding plane that they're found in?
The impact deposits themselves are not dated. The ages are derived from the rocks and sediments around them. For the younger ones, it's mainly based on microfossils in the sediment. And for the older ones, it's age dates from radiogenic age dates on things like volcanic rocks and minerals.
And is the size of the impact inferred from the thickness of the spiral bed?
In general, the size of the impact is inferred from an integration of the amount of material and the amount of iridium and things like that. But yeah, it's basically the larger the asteroid, the larger the crater it digs, the thicker the deposit ought to be. And if you've only got one, that's not a very good measure because there may be sedimentary processes that concentrate in one place or another. But if you've got a bunch and they're all telling you the same story, it's probably giving you a consistent story as to the amount of material. And in cases like the late Eocene and the Cretaceous Tertiary, we've actually got the craters, so we know pretty much how at least not necessarily the size of the asteroid, but the amount of energy it used to excavate a crater.
Thank you.
Okay. So there's a question in the chat, Frank. You can look at it, or I can read it to you. Whatever.
How do I get to the chat? I guess
at the bottom of your screen.
I have to exit this.
Yeah. Okay. I will. Well, yes. Do you want me to stop sharing your screen, or?
Oh, okay. Oh, stop share. Okay.
Okay.
So, and how do I get to the chat here?
At the bottom.
I see it. I see
in
it.
the middle, yes.
Okay. So, which one am I looking for?
From Mimi Anaya.
From Mimi. Is there any other mechanism on Earth that can make these spherules only impact? Well, geology is really good at making. Geology is really very good at making round things. So there are, for Simonson and his work on the Proterozoic ones in Australia, in his paper, he gives a lot of examples of things that are formed by volcanically and by sedimentary processes that make beds full of round objects. It's when you find things like quench textures and iridium and shocked minerals and things like that that you have solid evidence that it's formed by some sort of impact other than normal geological processes. But geological processes aren't going to fill sediments up with a lot of iridium and platinum group elements and very strange chromium isotopic compositions.
Okay, perfect. So the next one is by Gary. You can see the chat.
Okay, what depth was the bed found in the ocean? I'm not sure which bed you're talking about. If these are global deposits, they will be found at whatever water depth the sediment accumulates. In the Pacific Ocean, I've looked at 7 or 8 different localities, and they range in depth. From the water depth is from a few kilometers to 6 kilometers water depth, one of them. The depth of burial in the sediment also is different. It depends on how quickly the sediment was accumulating. At that site in Spain, that was buried under many kilometers of sediment. I have a site in the North Pacific where the sediment was accumulating very slowly, and it was buried under only 20 meters of sediment. So it really depends on how much sediment accumulates on top of it. But the deep sea drilling program can drill cores in the sediment at the bottom of the ocean. They've drilled all the way down almost halfway to the mantle. They can go many kilometers into the sediment in the crust.
Okay, so now
the depth of deposit really depends really on how deep the water was when it was deposited, or how fast the sediment was accumulating on top of it after it was deposited.
thank you. So I will ask Nick to unmute himself so he can ask the question.
Yeah, hi Frank. In your last slide, or next to the last slide, one of the layers of spherules had frequent flattened ones, all oriented in the same direction. I'm wondering what state they were in, what plastic state they were in, at what time, how do the flattened ones get formed, and how does that compare with the same sort of structures of flattened spherules in chondrite, or how might it?
Let's see.
Yeah, that's
This one here?
Yeah.
I don't really know how to answer that question.
Okay.
There's going to be some sort of compaction where, this is in a section that's kilometers thick, and it underwent very heavy hydrothermal alteration over a period of millions of years.
Okay.
And they don't look so flattened to me. Most of them look kind of roundish.
Well, the ones that are flattened are all flattened in the same direction.
Oh, they are? Okay. Well, I really can't answer that. This isn't one that I've done a lot of work on other than measuring iridium.
But this is probably something that takes place after they've cooled and been deposited on.
Oh, yeah. Any flattening probably occurs after they've been deposited and they're getting altered. Some, depending on the composition, some we've seen this in Tertiary Boundary. Okay, I just got a poll popped up on me.
Oh, sorry.
Like in the Tertiary Boundary, it's pretty clear that some compositions don't flatten nearly as much as the ones that are probably very iron and magnesium rich. Tend to alter more quickly, and so as the sediment compacts, the ones that probably have more asteroid material are getting flattened right away, whereas the lighter colored ones stay around a lot more easily. And so the degree of flattening can also depend on the composition of it, how quickly it alters. Because different minerals will alter at different rates.
Okay, thank you.
Thank you, Frank. There's another question in the chat from Mimi again.
Okay.
She asked about deposits from the moon.
Okay, so what am I looking at here? How about spherular deposits from the moon? They've been found in moon rocks? Paul Warren would be the best person to ask about that. But I know that there are a lot of glassy spheres that are found in lunar rocks. Paul would definitely know a lot more about that. And some of them form from impacts, and some of them form from volcanic fountains. If you're asking how about spherules from the moon on Earth, no, I don't know of any significant evidence of that.
Okay, thank you. Yes, Gary, can you unmute yourself?
Yeah. Stand by.
Yes, we can hear you.
Hello?
Yes?
Yes?
Hi, it is Paul Warren.
Ah, Paul, hi. Would you like to answer the question?
Okay, can you hear me okay, Frank?
Yeah.
Yeah,
Okay.
Gary.
Yeah, sorry, wrong button. It goes to an estimate of the volume in the KT barrier. Is that, if you can project how much material is distributed around the world, is that consistent with the impact itself and your estimate of how much material was ejected?
Well, there are varying estimates of the size of the impactor. Of course, the crater is going to depend more on the energy of the impact than on the actual size of the asteroid. And so a smaller asteroid that's going at higher velocities will make as big a crater as a larger asteroid at lower velocities.
Yeah.
The original paper by the Berkeley group, the Alvarez group, came at it from a lot of different ways, like the amount of iridium and the thickness of the deposit. and they came up with an estimate of 10 kilometers based on just a couple of data points. And in fact, in their preprint, they calculated it one way, and in the final published paper, they published another way, and the numbers were actually totally different. They still came up with 10 kilometers. So 10 kilometers is, in a lot of ways, just kind of a guesstimate. And there are other ranges of estimates. The impact people who model impacts, according to their models, it would take a much larger than 10 kilometer diameter asteroid going at 10 kilometers per second or 20 kilometers per second to make Chicxulub.
Okay, so what's your estimate on the total cubic meters of rock that was ejected from the impact?
The total cubic meters of rock, I can't tell you, because so much of it, most of the mass is in that blanket right around the crater.
Right. Okay.
What I can't, but let me just finish the answer though. The impact guys, like Jay Malash, have come up with models that suggest the asteroid must have been like 18 kilometers, which I think isn't really possible. Myself and a couple other workers have looked at the amount of iridium in the Cretaceous Tertiary Boundary and the amount of osmium isotopes in the Cretaceous Tertiary Boundary, and we come up with an estimate more on the range of 6 to 8 kilometers. So, 10 kilometers is a nice ballpark estimate, but by using the amount of iridium and osmium in the sediment, we come up with 6 to 8 kilometers, which is a lot less mass. And the impactors come up with a number much bigger than 10 kilometers. So, 10 is a nice ballpark number, but nobody really knows for sure.
Mm-hmm. Mm-hmm. Because this goes to an interest that I have in the DART mission, that if the rock is too big, if we'll ever have success in diverting it. So I wondered if you could comment on that.
Well, I'm not very expert on that, but my understanding is that the density and cohesiveness of asteroids and comets may be very different from one object to another. If something is just kind of a loose sandbank or something like that, it might be a lot harder to divert it than if it's a piece of solid rock, like part of an asteroid.
Yeah, yeah. Thank you.
Thank you, Gary. So let's.
One more question.
Yes, but first let's hear from Paul, then Candace, then Peter, and then I get you, David. Sorry. Paul, did you wanted to comment something?
Well, I'm sorry I've missed a lot of this talk because we had a lizard, an unwelcome guest in our living room. We spent, you wouldn't believe how much work it was to get him out of there. Anyway, that's how I spent most of the last hour and a half. But you mentioned impact glass and the lunar samples. Yeah, we find them really useful because we want to distinguish material that's of regolith derivation from the surface intimately mixed up and guarded part of the moon. And one of the best ways you do that, quick way of doing that, is to find those impact spherules, glass spherules.
Okay, thank you. Then Candace, you can.
Hi there. Can you hear me?
Yes.
Louder.
It's really good to see everybody. Frank, it's been a wonderful talk. Can you get any idea of what type of material the impactors were? What type of asteroids in any of the cases?
Well, the best information in that regard, well, there's a couple of ways. For the Cretaceous Tertiary for chromium isotopes tell you a lot, because chromium isotopes can distinguish Gary Shkolyakov, who I'm sure you know, or Shkolyakov, analyzed chromium isotopes in Cretaceous Tertiary Boundary, and it's pretty clear it's some kind of carbonaceous chondrite.
Right.
And you probably know that we found this piece a few millimeters across, and by looking at that, our best guess based on the very altered mineralogy of that it might have been some sort of CV or CR or something like that, a carbonaceous chondrite with a significant amount of metal in it. Beyond that, it's hard to say. All of the early Archean ones that have been analyzed have had chromium isotopes like carbonaceous chondrites. The late Eocene has chromium isotopes like an ordinary chondrite.
Okay.
And so that's the best way of getting a handle on it, basically. if you don't have an actual specimen, which in most cases you don't have a specimen, you've got to resort to some sort of isotopic measurement.
Thanks.
Thank you.
I also think the Proterozoic ones, a couple of the Proterozoic ones have been analyzed, and they also come out to be ordinary chondrite.
Okay, there's a question from Peter Utas in the chat.
Oh, okay, how practically do you locate, i.e. found a spheral layer just millimeters thick in a deep sea core? Well, you do it, you have, somebody has to tell you based on fossils or something about where the sediments are that are the right age. You can't just take several kilometers of sediment and measure iridium in the whole thing. You have to have somebody that will narrow it down to you to some manageable number. There's one core near 577, actually 576. It's a clay core. It doesn't have any of those nice little microfossils, but a woman who did research done at Scripps, who studied fish teeth, was able to tell me within 2 meters in this clay core where she thought it was. And I analyzed iridium across 2 meters of clay, and I found it, and that's the core where I picked out the piece of the asteroid.
Wow.
There's this nice Hershey chocolate brown sediment with almost no fossils in it except a few fish teeth. And by measuring iridium in it, I found out where it should be, and I went back and looked at the core, and in this nice chocolate brown sediment, there was this light colored rock that was a few millimeters across, and it was a piece of the asteroid.
Well, thank you, Frank. It's a very interesting talk.
Now, David, you can ask your question.
Unmute.
Yes, David Michaels.
David, unmute.
My question was asked. It was the type of material the asteroids that impacted.
Oh, okay.
Okay.
I unmuted you.
So,
Yes, I've got controls here. I'm in charge.
do you have any more questions?
I suppose one other thing on the materials, what about iron content of the impactors? Anything consistent on that or any interpretations?
Iron doesn't really tell you a lot because there's a lot of iron in earth rocks and stuff too. It's not nearly as rare as platinum group elements like iridium. In general though, because the asteroid certainly had a lot of iron in it, like the Tertiary Boundary, the lighter colored ones don't have much iron in them. They've got a lot of calcium and aluminum and stuff like that from the sediment. The darker colored ones that have a lot more asteroid fraction in them have more iron, but elements like iridium are much more diagnostic than iron is.
Thank you.
Okay. Anyone else? If not, I will invite you to unmute yourself and give Frank an applause and thank him for the
You can't just do an emoji applause?
Yes, you can also do an emoji applause. So thank you, Frank. And thank you everybody for joining us today. And yes. Sorry? Someone was talking? No?
Oh, what's your next project in this endeavor?
Oh, I'm not doing a lot of very detailed research. Most recently, I've been trying to compile all my samples from the Altanin asteroid impact and get them packaged so that I can stick them into the meteorite collection.
Great.
I hadn't told anybody that.
Okay.